All right, so here's part 4. That looks a little bit better focused to me, so hopefully you can see that just a bit better. All right, for number 11, we are looking at ethanol. Ethanol, we've given its melting point here and its boiling point. We're given the enthalpy of fusion and the enthalpy of vaporization and specific heats. And what we want to do is calculate the heat required to convert 21.6 grams of ethanol from a solid at negative 205 degrees Celsius, so it's below that melting point, so it's a solid, to a gas at 78 degrees, okay? So we're going to heat it up, it's going to become completely into the gaseous phase, and then it's not going to be heated anymore. So what I'm going to do is break this down into a couple different steps here. All right, first step, step number 1, incidentally, each of these steps will be 1 point. All right, we're going to have the process of heating up, I'm also abbreviating this ETOH, this is ethanol here. We're going to talk about the process of heating up this solid ethanol from negative 205 degrees Celsius to negative 114 degrees Celsius. So we're essentially heating up this solid frozen block of ethanol up until its melting point. All right, now in order to do this, we need to multiply our mass of ethanol that we have by our change in temperature, our delta T, from, where were we, 205 to negative 114, which is 91 Kelvin. All right, that's the total delta T. And we also need to multiply that by the specific heat now of the solid phase. Specific heat is here, 0.97 joules per gram Kelvin. Let's just make sure we've set this up correctly. Grams cancel, Kelvin cancels. I'm left with joules. Looks pretty good to me. All right, so I do this. There's only 2 significant figures here because of the 91 Kelvin. So I've got 1.99, that's a non-significant digit I'm just including, times 10 to the third joules, or 1.99 kilojoules. Okay? All right, so I've heated up my frozen solid block to get to the point where I'm ready to now change the phase. When I'm changing a phase, I need to use, from solid to liquid, I need to use my enthalpy of fusion. Now, enthalpy of fusion is given in kilojoules per mole. So what I'm going to need to do, this is the second step, but it's worth 1 point. What I need to do is convert 22.6 grams of ethanol into moles of ethanol, which I can do easily enough using the molar mass. Okay. I'm then going to multiply moles by my enthalpy of fusion, 5.02 kilojoules per mole. Grams cancel, moles cancel, I'm left with kilojoules, 2.46 kilojoules. All right, next step. Next step is also worth 1 point. We've got to go from that liquid ethanol, and we're going to heat that up until 78 degrees right before it starts to change phase. So, 22.6 grams of ethanol. My delta T is 192 Kelvin, my delta T. Multiply that by the specific heat, 2.3 joules per gram per Kelvin. Again, I'm just going to cross this out, make sure I did everything correctly. I'm left with, I'm just going to convert directly to kilojoules here, even though I'm in joules. I'm doing the conversion kind of in my head to kilojoules, so it matches. 9.98, with a line right there, non-significant digit, kilojoules. All right, next step, also worth 1 point. Now we've got to take this ethanol and we've got to move it from the liquid phase into the gaseous phase. So 22.6 grams of ethanol. I've got to convert it, grams to 1 mole, because my enthalpy of vaporization is given in kilojoules per mole. Multiply that, kilojoules per mole. Grams cancel, moles cancel. I'm left with kilojoules, which is what I want. 18.90 kilojoules. Okay, so now I've got the heat for every step. Okay, so what I want to do now is find the total. So I just add it up. Kilojoules, 2.46 kilojoules for this step, 9.98 kilojoules for this step, 18.90 kilojoules for this step. Okay, I add them all together. All right, now notice this is including some non-significant digits, but I just had to include it here, to make sure that I'm doing due diligence with my math and all. Okay, but I'm adding, so I'm only going to go to the place where I'm certain, relatively certain about my sig figs, which is the 10th place here. So I get 33.3, this is actually 3 kilojoules. Again, this is not significant, so my answer, 33.3 kilojoules. Great. All right, let's look at number 12. Based on the following information, which compound has the strongest intermolecular forces? Explain using both the heat of vaporization and the structures. Well, we can look at the heats of vaporization here. The one that's got the highest actually should have the highest forces. So that would be water. All right, so H2O has the strongest, IMF. That's worth 2 points. And again, it says which is the strongest and also which has the strongest, and then explain using this and this. So you get 1 point for saying it has the highest enthalpy of vaporization, requires the most energy to change phase. And you also get a point for talking about the hydrogen bonding that's taking place. Okay, hydrogen bonding happens all the time with these guys. There's 2 hydrogens available to hydrogen bond. Great. Let's write my name here. Bruce's name on the paper. Write it here too, Bruce Banner. Okay. All right, on to number 13. This is my attempt at injecting some biological relevance into the conversation. DNA double helix represents a twisted ladder with opposite base pairs connected by hydrogen bonds. This is an AT base pair. This is a GC base pair. Circle the base pair that is more stable when heated. Well, this guy, CG, is more stable with heated. That's 1 point. And the reasoning is 2 points. More hydrogen bonds lead to stronger intermolecular forces, more stable, what are we going to call that? More stable base pair. Cool. All right, number 14. Consider the diagram. The phase changes, B to C and D to E, are not associated with temperature increases. Explain why. For 2 points. Well, heat added during these phases goes to breaking IMFs, intermolecular forces, and changing phase by moving molecules farther apart. 2 points. All right, number 15 of my exam here. The melting point of metals across period 5 of the periodic table rises as you move to the right and then begins to decline. Explain this trend using melting points. Well, I have to explain this trend using molecular orbital theory. All right, so here's what I'm going to say. As you move right along the period, bonding MOs fill, leading to increased bonding strength and high melting points. Then, now notice I'm using complete sentences here. You didn't have to do that. Then, antibonding MOs fill, leading to weaker bonds and lower melting points. All right. So So you got really 2 points for talking about this piece of it, that bonding orbitals were filling, you had increasing strength, and then 2 points for talking about antibonding orbitals filling. For number 16, for each of the following, indicate if it is a substitutional alloy, interstitial alloy, or compound. All right, for this guy, we've got iron and silicon. In this case, it is an interstitial alloy. Did I spell that right? Interstitial, yeah. All right, so there's a significant size difference here. All right, so here we go. We've got now iron and nickel. This is a substitutional alloy. All right, you can see that, just looking at the proportions. Let me see if I've got a table handy here. Let's see, yeah, this will work. All right, here we go. We've got iron and nickel there. You can imagine these guys are pretty darn similar in size, so having one of them kind of wedged into, near the other one would be a little bit difficult to fill those empty spaces. So similar in size, substitutional alloy. And this one is actually a compound, an intermetallic compound, because it's present in whole number ratios. All right, this is actually a homework problem, so hopefully you remembered that from your homework. All right, number 17. If I want to modify silicon to make an N-type semiconductor, an N-type. N-type means that we need more valence electrons. Suggest an element that could be used as a doping agent and explain your choice. Okay, now the one that I'm going to choose that I think makes the most sense is phosphorus as my doping agent. All right, here's silicon. I want something that's got more valence electrons. Phosphorus is right here. Okay, this has 4 valence available. This has 5. It's a natural one to choose. Okay, so for my reasoning, that would give me 1 point if I had a reasonable, logical one to choose. You don't have to choose phosphorus. Anything with more valence electrons would work. All right, so I'm going to say phosphorus has 5 electrons in the valence, 2 silicons 4. Lents. That was a horrible spelling job I did there. All right, so, but really any element that has more valence electrons would be okay. I mean, it's probably not practical to do, like astatine or something, that's radioactive, or polonium, but I guess technically that would be okay. Although those, when you get down there, those really do take on more characteristics of metals, so they probably wouldn't be good choices. But in any case, I don't think anybody did that. All right, number 18. How do crystalline solids differ from amorphous solids on a molecular level? This was a question that came from the practice exam. So if you did the practice exam, this should be 2 easy points for you. Crystalline solids have an orderly, repetitive structure. Crystalline solids, orderly, repetitive structure. Amorphous solids have no organized structure. All right.